done with this one.
Okay, we're up on YouTube. If you guys want to lecture later, you can. All right. We're going to talk about technical specifications and administrative controls. I just put the questions in the quiz today because I wanted to make sure that I was going to go over all of them, because I noticed that the lecture, and I'm using a lecture that the previous reactor supervisor used, it didn't have all the information, which is probably why they've had some trouble with the exam and students passing it. As I noticed that they did a whole lot of details, but then when I was going through the exams, there were some questions that weren't covered. So I'll skip back a little bit. I'll go over the presentations and we'll actually go through the TSR document. But since I got the quiz questions up late, I did go ahead and extend it a couple days as well, because you were supposed to have them up since Monday and it's now Thursday. So you have a couple more days to look at the quiz. So made that quick change for you guys.
And is that last quiz, the start quiz, is that repeatable now? No loss of points?
So what I'll have to do is I'll probably have to a second one that doesn't feed into your, and I have not done that, but I can. I'll try and do that right after this class. And that way, and the reading. So for the textbook, I was doing the reading just to refresh our discussion. They're very specific to a PWR, but I still really like he describes a bunch of the reactor physics concepts and how it plugs in. So the conversation he has about K-effective, reactivity, control rod work, all of that information, I think it's mostly in chapter 4 right now, it might have been chapter 5, is exactly what we're going to hit again when we start talking about reactor theory. So I really like that you're kind of getting an introduction to it, because it does permeate some of the reasons we have our safety limits and limiting conditions for operations. So hopefully you guys are getting a rough idea, and then we'll delve into it a little bit more when we pull up the Read Robert Byrne text, so that you're actually able to perform the reactor theory calculations that will be on the license exam. And even when we do that lecture, we're going to skip a little bit of the background. Marcus and Sam, you'll get more of that when we do our reactor theory class. So I'm going to tell you this is how things are in this class. And in 251, I think it is, I'm going to tell you why it's that way. So for this class, I'm telling you what happens. You'll get the theory behind it later in your program. Sue, I'm sure you'll get this in the nuclear engineering department in their classes. And Christy, you have hopefully already had quite a bit of this theory. But hopefully the textbook kind of helped explain. Then when you were seeing references to that material in the SAR and the TSR, it was kind of syncing together. Was there anything that really stuck out in the TSR that you're like, I have no idea what this is even talking about, or in the SAR?
So one thing I saw with the TSR is it refers to the reactor as a low power reactor. Is it the same as a subcritical reactor, or are they different?
They're different.
Okay.
So a low power reactor is going to be generally anything that is below commercial power levels, right? A subcritical assembly does not get critical, which means it can't actually produce any power. So that's a zero power reactor. So the zero power physics reactor, Zipper, at MFC, that's now removed, but we still have that facility that you guys walked by on the tour. It was a critical assembly that never actually went critical and produced power. So the subcritical assembly inside the reactor lab in the subcritical assembly room doesn't produce any power because it doesn't go critical. You have to go critical to start producing power.
Okay.
That make sense?
Yep.
Okay. Your box lit up, Christy. Did you have a question?
No, I just took my headphones. I was getting a headache.
Okay. Jax did that too. He wasn't saying anything and it highlighted like you were, so that's fine.
Oh,
Any other questions that you're like, hey, I don't really understand what this is talking about or where this information is, what's based on in the reading you guys have done so far?
There was one other thing that I asked you about when I was going to this song. There is something, I'll try to find it in my notes and bring it.
Okay.
But there is one part where they started explaining the process and I was just, it kind of felt like it was out of the blue.
Okay. Okay. We can cover it if you got that question. Okay. All right. So in this lecture, they also talk about the emergency plan. We're not going to cover the emergency plan right now. So don't worry about reading those slides in the lecture that ATR gave us, but they pull out the wording exactly that we need to look at for some of them. So we are gonna use this a little bit. Okay. So technical specifications. The TSR is ordered. So first of all, the TSR is an appendix to the safety analysis report. Okay, so all of the information in the TSR is because of what's in the SAR. Okay, so it's very important that you understand that relationship. We have the safety analysis report. We know what our accidents are that are concerning. And because of that, we know what we need to control and make our technical specifications for our TSR, okay? It is ordered so that first, it covers a list of definitions. Most all of them are important, but I can basically guarantee you that either on the written exam or on the practical walkthrough, you are going to be asked to define and explain the difference between a channel check, a channel test, and a channel calibration. These are really good things to know because it governs what action you as an operator will take when the procedure tells you to perform either a calibration, a test, or a check. So those definitions, we're going to talk about a few, but know those three. There was almost not a single version of the written exam, and I've seen several for several different years that didn't have that definition or some version of that question on it. I was asked that on my written test back at the University of Missouri, and I was asked to explain it in person and the practical, both. So it is very important that you understand those because there's certain things you can and cannot do when each is called for in the procedure. And if you do the wrong thing, you've now invalidated your check or your test, which means that the information that that procedure is asking for, which might be related to a TSR, can't be validated, right? So if you don't understand those, you have the potential to walk into a TSR violation. After definitions, it talks about safety limits and the limiting safety system settings, okay? We're going to go over this. We've talked about the fact that the safety limit is our power and temperature, right? And that we protect that with our thermal fuse. We also have a few other settings. Limiting safety system settings are designed to automatically protect the safety limit. That's the relationship here. You have a safety limit. You cannot violate that. To ensure that you don't, you have limiting safety system settings. Okay? Then it talks about limiting conditions for operations. these are the things that you have to observe in order to be allowed to run the reactor that keep you from busting through a limiting safety system setting, right? So there's a hierarchy. This is at the top. This is under this to protect that. These are under this to keep you from reaching that. And then these are under this to ensure that everything meets these LCOs, okay? Limiting conditions for operations will include our reactivity limits, our limits on experiments, our limits on shielding and radiation monitoring, and the required control and safety systems that have to be operable for us to engage in operation. Okay? Then, for each one of these limiting conditions for operation, there will be a corresponding surveillance requirement that says before you can operate, in a procedure, you operator must go and survey that these things, these LCOs, exist and are in place. And you're going to have a place that you record and document that you've actually gone and surveyed that the LCOs are in place. Okay? Then there's design features. These are physical or electronic pieces of how the reactor is designed that are things that you have to ensure stay that way, so they're protected by TSRs, right? You can't operate the tank without water in it because that's shielding. That's a design feature of the reactor that it's supposed to be there to create that shielding. Therefore, you have to protect that water with a TSR. Okay? And then last is the list of administrative controls. And these are basically all the things that we can't put a system setting or a physical system in place, but we still need to have rules for. The big thing that you really need to understand from the administrative controls is going to be your responsibility for maintaining your license. So the training and ongoing health certification that you as an operator will have to ensure that you complete, and the staffing requirements. There's certain minimum numbers of people that have to be at the plant for you to operate it. And you can't start operating, even though you're a licensed operator, without following that administrative control.
So if you're at school, what would be the amount of people that have to be there?
There has to be an SRO, there has to be an RO, and then there has to be one other person in the control room. So that SRO has to be within 20 minutes of campus. The RO has to have another person, whether that's another RO, an SRO, the reactor supervisor, a trainee, or a certified observer, and all of those are defined. But you have to have two people. One has to be an RO, an SRO has to be on call, and those are your staffing requirements. Okay. So, here's our definitions. Because this has got some orange. Do you guys want me to turn this front light off? Or you have it on your screens? You're good?
Yeah.
Okay. So, channel calibration. An adjustment of the channel so that the output responds to an acceptable or expected, I don't know why they put acceptable, accepted or expected range of known values. Calibration is the only time you can actually change the channel. So if you're getting a reading from that channel and you know it is wrong because a discriminator or a calibration tool has not been set correctly, you can't just change that unless you are in a procedure that tells you you can do a channel calibration. So when you do a channel check or a channel test, and you get results that are wrong, you can't calibrate the channel to get the right results. You have to take the results of the test, right? A channel check is a qualitative verification that the channel is performing correctly. So this is going to be that you're going to go take a reading from it, and it's going to correspond to what you should know it should say while the reactor is off, right? So you're going to do a ton of channel checks as part of your pre-startup checklist, right? And that's essentially doing a qualitative verification that the channel's on. This and this are off, so those relays should make sure that this channel is now on. Qualitatively, is it? You've done a check, okay? A channel test is an introduction of a signal to verify that it's operable. So now you have a radiation detector, and you've done a check. You know that it's on, and you can hear its audible counting. You don't know if it's calibrated, but now you're going to test if it's operating in its correct range. You're going to hold a test source up to it and receive a radiation alarm, right? You've now tested your channel. If it alarmed too early, or it alarmed only when you had a larger source than is required, you're out of calibration, but you can't fix that until you enter a procedure that allows for channel calibration. You've just done a check and then a test, and then calibration has to be a separate thing. Does that make sense? Okay. And then the definition of operable: the component or system is capable of performing its intended function in its normal manner. So you may be able to pass a channel check, but if the channel is not properly calibrated, it's going to fail the channel test, and it's not operable, right? Okay. That makes sense to those of you online? Any questions?
How often do we go through this process? Is it every time, or is it occasionally?
It will vary. Channel checks, you're going to have a list of channels that you have to check every time you start up, periodically at certain powers, and when you shut down. Tests, typically there's some periodicity specified in your surveillance requirements, as well as calibrations, right? So we are required to test the seismic scram annually. So every year we test that when a certain amount of vibration is detected, it will cause a scram. And if it doesn't, there's a procedure to do calibration, right? And then we assume it's good for a year. So some things will be daily. Sometimes it's things that you're going to opt on an operation basis, right? You won't do until you actually operate. Some things will be done quarterly, monthly. It just depends on what the procedure specifies for those.
Okay, and do we put the channel check and the test and calibration results in our operator logs, or?
Most of the time with channel checks, you're wanting to verify, they're going to give you a checklist, right? So we talked about that as one of the control documents. You're going to have a checklist that goes through it. As part of the procedure, it's going to say either complete pre-startup checklist or perform this step and record the result in your pre-startup checklist, right? Either language does the same thing, right? And then you're going to take your pre-startup checklist and you're going to have to get the SRO to sign off that you can start operating, right? Okay. The next set of definitions talk about the definitions of experiments. I'm not going to go over this in detail because I'm going to have Jonathan kind of talk about the experimental facilities and show you guys how you would put in experiments and walk through some of the procedures. And he's going to go through those definitions in a little bit more detail when he does that. But understand that very specifically the types of experiments and the different modes of experiment, secured and unsecured, are actual TSR definitions. And so you have You have to understand if an experiment is secured or unsecured, because then you understand if you can leave the reactor in its shutdown configuration, right? You can't have an unsecured experiment and call the reactor secured, for example. Does that make sense? Okay, let me make this note. Okay. Okay. Reactor shutdown, reactor secured, and reactor operating are also definitions you have to know. Reactor shutdown, all rods are fully withdrawn or core is split, right? This can be shut down after an accident. And the power key switch is in the off position and the key is in the hands of an SRO. So not only do you have to have the rods out and have stopped our physical reactor from being on, you also have to have the console off, and an SRO has to have that key. Not an RO, can't be lost. The SRO has to have possession of it. Your reactor secured is what you're going to do at the end of the day when you leave, right? It has to meet the conditions of shutdown, plus no work is being done, right? So there's not ongoing maintenance, and no experiments are being worked on. Okay? So you could shut down the reactor and you could leave to go to class, but the reactor supervisor, who is a licensed SRO, is still in the reactor lab. Do you have to secure it? No. But when you all leave, at the end of the day, the reactor has to be secure. Make sense? Everybody online following? Okay. So, shutdown margin. It is an important definition. We're going to get into it more as we get into theory. But essentially, this is saying minimum shutdown reactivity necessary to provide confidence the reactor will be shut down. And then we have what we call the stuck rod criteria, which means that it can be shut down even if our most reactive rod doesn't scram. So what this is saying is all that fuel coming together with the control rods and the fuel disc in the center creates a certain amount of reactivity that allows us to go critical. When we put the reactor in shutdown, we have to know that there's not going to be any chance that it can go critical again without us as operators moving the control rods, right? And even if for some reason you can't get the most valuable control rod out of the core, it stays. The other two that can scram, right? We don't count the fine control rod, it doesn't scram, it doesn't count in any calculations ever. But our most reactive scramable rod is going to stay in along with the fine control rod, which we take no credit for. So 2 rods of the 3 that scram have to be enough to shut the reactor down by so much reactivity that we know it's not going to go critical. And the NRC gives us an amount that this shutdown margin has to be. Okay, and we'll talk about that, the regulation, and a little bit more of the theory, because you also have to be able to calculate this. Okay, but for right now, does that explanation make sense for what that is? Sue and Christy, does that explanation make sense for you guys? Yeah, okay. Good, good. Okay. You don't need to memorize these, but you do need to know that in a facility, 2 years, annual, semi-annual, quarterly, and monthly, don't mean what they mean on our typical calendar. They mean that plus the grace period, right? So a month is 4 weeks. 4 weeks plus a 50% grace period, 6 weeks. Quarterly plus a grace period, 4 months, right? So it is important for you to be able to tell the NRC inspector that our surveillance requirements have a surveillance time, and the actual time we have to perform that includes a specified grace period, and that you know where to look that information up. Okay? That 1% delta K over K, that is the minimum shutdown margin that NRC says we have to have, but we'll talk more about that. Okay, so we talked about safety limits quite a bit when we talked about the SAR, right? Reactor power shall not exceed 100 watts. Maximum core temperature shall not exceed 200 degrees Celsius. You must know those two, because as an operator, essentially every procedure, every system you touch is designed to prevent you from reaching either of those limits. Luckily, in our reactor, there's only 2. Commercial reactors can have 5, and then the corresponding LSSs and LCOs to match. So our reactor is pretty simple. There's only 2. Okay. To assure that automatic protective action is initiated to prevent a safety limit from being exceeded, our limiting safety system settings are going to be far below our safety limits so that we never reach them, right? Our limiting safety system setting to protect the safety limit on power is at 6 watts. So when our reactor reaches 6 watts, we're going to scram so that we never reach 100 watts. Does that make sense? The thermal fuse will melt at 120 degrees Celsius so that we never exceed the safety limit of 200 degrees Celsius. So this relationship between scram at this power to protect this power limit and core separation at this temperature to protect this temperature, this whole slide, you just have to know how this all works together. And you have to be able to explain it to the NRC examiner, that you understand why all of your systems are set at 6 watt and 120 degrees, and how that protects your safety limit. That is like the thing. Anyone have any questions on that relationship? Okay. LCOs. These ensure that the reactor can be shut down at all times, right? These are our actual limiting conditions to ensure that our LSSs are able to function to protect the safety limit, okay? And so what we're saying is we're putting a limit on excess reactivity, which effectively physically limits the core from producing as much power as we would need to get to the 100 watts, right? We're not going to put in enough reactivity that you could accidentally throw all the control rods in at once and suddenly create a super critical reactor that jumped up to 100 watts, right? If you throw all the control rods in, it's going to produce a power much lower than our limiting safety system settings, right? And then, of course, we have to have at least 1% delta K over K for shutdown reactivity. And we have to meet our stuck rod criteria, right? So if the highest worth rod, whether it's the course control rod or safety rod 1 or safety rod 2, is stuck in the core, those other 2 are going to be enough to ensure we're still at our shutdown reactivity. Okay. Then the TSRs have some specifications for our different systems, right? It tells you how fast they have to scram. in order to keep that power from rising if we happen to get super critical at a level we don't want. It's controlling how much reactivity is in each rod. It is telling you you have to have a manual scram. If you don't have power in the facility, you're going to automatically scram. You're going to have a radiation monitor that's operable. And whenever the reactor is not secured, you have to use that radiation monitor, right? And that all of the safety instrumentation shall have specified limits, and then there's a table in the TSR. I'm not going to read every single value, but this is what you're essentially going to go through when you do your channel checks, right? You're going to make sure each one of these systems is at the correct set point. So you'll become familiar with this as you go through the procedures more and more. But the important thing to know is those set points come from the TSRs. Okay. Then there are some interlocks where you can't move control rods or turn on the reactor until certain conditions are met, right? So your rod drive, you've got interlocks so that you can't insert more than one control rod at a time, right? Only one rod at a time goes in. We don't have banks. Some reactors have control rod banks. Every one of our control rods moves independently, okay? So there's an interlock to prevent you from grabbing the up switch on one and the up switch on another and pushing them both up and having them both move, right? Your low level neutron count interlock on channel 1 ensures that you can't start up the reactor without having an accurate read of information at low power, so you don't start putting in too much reactivity too fast. Tucker talks exactly about that, right? At the low levels, you have to get a certain reading so that as you start going up, you don't suddenly hit supercritical and jump up super fast, right? That's what our channel 1 low level interlock is for. Shield water, we talked about, that's a design feature, right? Protects us from radiation. Therefore, we have to check that it's there. And so someone had to decide, can we have half the tank full? Can we have 90% of the tank full? And that amount was, it has to be within 10 inches of the top. So it has to be basically full. We talked a lot about the temperature feedback of reactivity, right? What is that concept? Either someone online or someone here in class, explain negative feedback coefficient of reactivity.
Negative temperature coefficient is what you're talking about? This is temperature increases, reactivity decreases?
Right. So the answer we got is that as temperature increases, our reactivity decreases. So what do you think would happen if we chilled the water in the reactor tank? Yeah, your reactivity would go up. So if we chilled the reactor water tank, it's possible we could exceed our excess reactivity limit. And then we would have too much reactivity. We would pass one of our limiting conditions for operation, and we'd be in violation of our TSR if we started up. So they did a calculation and said, as long as it's 15 degrees Celsius or warmer, we're fine. So there's an interlock on a temperature, bimetallic temperature strip in the reactor water tank. Okay? And then, of course, if we have an earthquake, and that tells you how big the earthquake has to be. Again, your limitations on experiment. Kind of the important thing to take away from all the experiment stuff, we don't put explosives in the reactor. And if you have corrosive or fissionable materials, they have to be doubly encapsulated. You don't want that to leak into the reactor. Those should seem pretty obvious, right? Nothing fancy about don't put dynamite in the reactor. Okay, I'm not going to read to you each one of the surveillance requirements. Do be aware that each one of these is going to feed back into one of our LCOs or our limiting safety system settings. There are some questions in the quiz that requires you to be able to look these up, right? I don't expect that you have every one of them memorized, but on the exam, if the examiner asks you about them, you would need to be able to say, this is where our requirements for our surveillances are, and here are the checklists and documents I fill out as an operator to ensure we're doing that, right? And as you go through the procedures and the maintenance procedures and stuff, you'll see the spots where you record all this. So know where to look up that you're required to do them. Don't memorize the whole list of when you do each thing, okay?
So if you do remember the list, would that be acceptable to tell them, or would you rather? You
Yeah,
tell them?
I mean, if you know it, say, I know that annually we have to verify the safety and control rod worth, and here is the form or the procedure that we do for this, right? So certainly knowing it is great, right? And especially because there's so few. But there's already quite a few things that I told you absolutely do have to have memorized. This is something where you need to know where to look. Okay. And then Sam, you had asked the question about how often, right? So annually, biannually, before every startup, right? There's the different ones. Okay. Design features. Our fuel will melt. Okay. The rods are going to be lifted by electromagnets, driven by a double lead screw assembly. If there's a loss of power, the electromagnets de-energize, the rods drop. Though they are also driven by a spring to make sure that they go at a fast enough time, right? And then the thermal fuse has doubled the density of the uranium dioxide so that it will melt, so that it will produce more energy and therefore melt sooner. And this information, I mean, this is good to know. It doesn't really melt. Technically, it softens.
Yeah.
But melting is a completely fine explanation of what's going on. You don't have liquid thermal fuse and liquid fuel at the bottom of your core. You have a softened thermal fuse. Okay? And then we talked about the fact that shielding is a design feature. Okay? And so understanding that these different thicknesses are required to make sure that the radiation levels in the control room are within the specified limits. Okay? One thing to note is that this is concrete barite. Okay? That block, it's a specific type of concrete that is at a higher density than like the normal concrete blocks you pick up at Home Depot, right? We've got a density of 3.7 grams per centimeter cube. Essentially what this does is it ensures that that concrete is very capable of blocking gammas. There's no gaps in the structure due to a lower density that allows any gammas to stream through it. Okay?
One thing was Marcus did bring up the thermal column filled with graphite blocks. Was that what we saw at the very top of the reactor? Or?
Yeah, so when you lift up the tank and look right inside, that's your thermal column.
Okay.
And this barite, this is a normal thing you'll see in shielding applications in nuclear reactors, right? This is just an industry trick to make it actual nuclear grade concrete. Okay? Okay. Administrative controls, there's a lot of statements of authority, and then there's this little chart, I think that's on the slides here, that kind of shows, yeah, how each of these fit together, right? So you guys are here, kind of down on the bottom of the totem pole, right? Under the supervisor, under the administrator, dean of the College of Engineering and the university officer, right? Then there's a reactor safety committee that reports to the dean and gets input and gives input to the administrator and the supervisor. And then there's a radiation safety committee that's under the university officer and gives feedback. So understanding how this structure ensures that no unauthorized or unevaluated changes are made at the reactor. We've got our checks and balances, right? You're going to be under the direction of a supervisor who's going to enforce the EU's procedures, who's going to work with the reactor administrator to make sure that those procedures meet the requirements of the reactor safety committee and the radiation safety committee. And if they don't do those things, the dean of the College of Engineering is going to be responsible for making sure that they do, right? Okay, minimum requirements for staffing: 1 licensed reactor operator in the room, 1 certified observer in the room, and an SRO on call within 30 minutes. A SRO will supervise all maintenance. Okay, so an RO can't do any maintenance without an SRO supervising, or any modifications that affect the reactivity of the reactor. Okay. TSR also requires that there are procedures for every one of the following things on this list. As we go over the procedures, you will become familiar with them, okay? The NRC requires that they are notified when certain things occur, okay? If one of the reactor protective systems failed, if you operated without checking that your LCOs were actually present, you have to notify the NRC. If you discover abnormal degradation, something you weren't expecting, like your aluminum starts rusting, notify the NRC. Reactivity anomalies: shutdown margin is less conservative than previously stated, you exceeded a reactivity limit, so you operated when that water was chilled, notify the NRC. Failure or malfunction of anything that affects the safety system that protects an accident analyzed in the SAR, notify the NRC. Error or procedural inadequacy, which actually affects safety systems, notify the NRC.
So that part they're replacing right now, they had to notify the NRC for that?
Yeah. Yep. If you find any errors in the SAR or TSR, or if you have to remediate structure SSCs, structure systems and components, that SSC abbreviation is used really commonly, because you find out that something that you assumed was protected in the SAR is actually less conservative in real life, notify the NRC. And if you ever melt the thermal fuse, notify the NRC. Okay. To obtain an RO license, you must complete at least 6 months of training. You must pass an NRC administered exam. You must pass the operating and oral exam. You must complete an FBI background check and submit a medical evaluation. For an SRO license, you have to have at least 12 months experience as an RO or a bachelor's degree, and you have to pass the NRC exam, which includes the background check and the medical evaluation. You also have to requalify with an annual written and operating exam administered by an SRO or reactor supervisor. Reevaluate your medical status every 2 years. Get a renewal from the NRC every 6 years. And every quarter you have to operate at least 4 hours, plus continuing education quarterly. Okay? Those lectures will talk about any updates to the procedures or the SAR that are happening just as part of normal facility procedures. Okay?
So with the reactor down right now, like it is, if that was down for a quarter, everybody would lose their license?
So there are some exceptions, right? You can perform maintenance and that counts towards your operation hours, but you still have to do a startup and a shutdown. So if the reactor is not allowing you to do that, you can get a little waiver from the NRC that says, due to an extended outage, I missed this, I will be able to do it in this amount of time. So you don't automatically lose your license, but you do have to pay attention if it's going to be out for a quarter. which is actually 4 months per our definitions, right? You would have to do something to work with the reactor supervisor to make sure the NRC is aware that you're going to miss that, but you're going to make it up because of circumstances outside your control, right? Okay, and then this requalification program is actually specified by the NRC, and then there's a few other things, right? You're not going to ingest alcoholic beverages or take illegal drugs. And for ISU, you can't ingest any alcoholic beverages within 5 hours of operation. Okay. So let's look here at the actual TSR document. Did you guys all get a chance to start the reading? Yeah. Online, did you guys get a chance to start the reading? Okay. So it's going to go through each one of those things in a little bit more detail, okay? And give you the actual wording rather than the summary. And in this presentation on the administrative controls, it really just lists the exact same things from the administrative control section. But there's a couple of little notes pulled from the procedures that are good to know, right? So here, you have to physically be at the controls. An SRO can count reactor maintenance towards their hours, but they still have to do start up and shut down, right? So that's what we just talked about. And that counts for SROs. So note that as an RO, you have to be at the controls. Okay? And then here's that list of rotating lectures and topics that you have to get exposed to quarterly. The NRC SRO will do the annual facility exam prepared by a reactor supervisor or reactor administrator. As they prepare them, reactor supervisor and reactor administrator don't have to take them, okay? Can't use a PA, has to be a licensed doctor. Should have said that on your form, right? And then you have to go get and redo the whole oral, written, and operating test by an NRC examiner every 6 years. And then it talks a little bit, again, about the language for what the procedures do, the reactor safety committee, which evolutions need procedures. Again, this is all directly the wording from the TSR, but a couple of these little notes are specific from the procedures and are just good extra information, though they won't be on your TSR quiz because they're from procedures. But it's good for you to kind of see some of the details, right? So I'd recommend kind of just reading through some of those notes. And then we get into the emergency plan, which we're not going to cover right now. We'll go back to that. So, any questions on our TSRs or our administrative controls?
I have a question.
Hang on 1 second, Christy. Sam's asking a question in class.
For the school, have like a hand-drawn paper for this is where the building is, this is where we shut down. Would it be possible to get like a new source spec? That's very hard.
I can ask Jonathan if they have one. They may not have one because that's what they have in the SAR, right. But I'll ask. If you send, well, you guys are going to see Jonathan tomorrow. Yeah, ask Jonathan if he has an updated drawing. That's better. Okay, Christy, what was your question?
Did you refer to one of the rods as a stuck rod?
Yes. So there's a stuck rod criteria. So the course control rod, safety control rod 1, and safety control rod 2 are all scrammable, right? And our fine control rod does not scram, right?
Right.
So we don't take credit for any safety anything with the fine control rod. It's not a part of safety systems. So of those other 3, safety rod 1 and 2 and the course control rod, one of them is going to have more worth than the other. And when we shut down, we have to assume that that rod that has the most worth gets stuck inside the core and does not scram out. And even with only 2 of them, the 2 least worth, we're still fully shut down. That's our stuck rod criteria. So it's not that one of the rods is specifically a stuck rod. It's that whichever one is highest worth, we have to not count it per our stuck rod criteria. Does that clarify for you?
Yeah.
Okay. Awesome. Sue, any questions? So our excess reactivity is actually smaller than our TSR limit, right? So that 25% is less than that 65%. What it's saying is what we actually have is that much below what the limit is. So that's a minimum that's somewhat below our maximum, right? Does that make sense? Okay, all right, awesome. Okay, well, that quiz is up. I'll go in my office and open up the STAR quiz. I'll open up a version 2 that won't count towards your grade, but you can take just to study and keep getting access to the questions. And it'll have no limit and it'll be ungraded. So especially before we go to take the written exam, that'll be a really good study tool for you guys. And then you guys have the TSR quiz, TSR and administrative controls quiz this week. And then next week we should have a couple more quiz questions from the assigned reading, and we'll be talking about, oh, let me see here what our topic is next week.
For week 6.
Yeah.
Reactive theory and radiation.
Yeah. Yeah. So we'll have a reactor theory quiz, which will be the theory questions from the exam, and then some theory questions from the reading, because he just has a good way of explaining it. And there's this Read Robert Burns book. It's what I'm going to use to kind of illustrate, because the sample questions in Read Robert Burns are exactly the kinds of questions that are on your NRC license exam, and they have examples that walk you through them. I'm a little worried with only an hour that we may not get through all the theory I want, and so it's possible that I might, depending on how well you guys are going through the procedure walkthroughs, I might take some of the procedure time and turn it into more reactor theory time. But I'll just kind of check with you guys how well you think the procedure walkthroughs are going, if you feel pretty confident and we don't need to lecture over them in as much detail.
And would that be like on Tuesdays or Thursdays like this at time, or would it be when we're supposed to meet with them?
So your procedure walkthrough should be happening with Jonathan,
Right?
right? And so I was going to also lecture on the procedures just to make sure that some of the ones that you may not see every time you operate, you've at least been exposed to. If the procedure walkthroughs, you're getting through some of those as well, I might just take away a little bit of time, just kind of ask you if you have questions, make sure you're aware of it, and then we'll jump into some more theory on those days. How is the operation time going with Jonathan? I know it sucks the reactor is not actually operating. Is everyone feeling like they're getting exposure to the facility?
I thought it was pretty great. Last time we went, we explained a lot of the little parts of components. It's hard to see on the start. Kind of just walk us through like the temperature thing, explain that a little bit, why we can't operate in winter as much as during summer.
Okay.
Which seems kind of backwards, but
right, doesn't it?
yeah, you went over quite a bit with this.
Okay. Sue and Christy, are you guys feeling pretty good about the lab time you guys get with Jonathan?
Yeah, we got through the second we got through pre-operational checks last time. So we're at pre-start data.
Okay. So you guys will probably get to go through the pre-start checklists tomorrow.
we actually finished with them like 20 minutes early just about. So, going pretty fast.
Good. Okay, well, awesome. All right, we'll knock it out there today. Thank you guys. And Sue, like I said, if there's anything you need me to sign to switch it to that pass-fail grading, just let me know. I just haven't had a student do that before, so I don't know what the process is.
So on the midterm, it says we'll have a graded reactor control manipulation.
Yeah. So Jonathan and I are brainstorming about that right now. There's a couple things going on with that detector that it may possibly be fixed sooner than he thought. We are also considering using the simulator, which is allowed. I'm just a little worried that it's a 4-loop PWR and there won't be something simple enough to be equivalent to what you do at the AGN. But I'm working with my intern who's helping program those to kind of try and come up with something that would be synonymous with the AGN. And then we also could potentially grade you doing it as a walkthrough, like you've been doing with Jonathan so far, like perform the pre-startup checklist, right? You're allowed to do that like you actually would, and we can grade that, and you just didn't actually turn the reactor on. So Jonathan and I are working on that. If we make any changes, it'll be in your favor. It'll be something easier than what we'd originally designed because the reactor broke, but we'll give you more details as we get a better plan.
Okay.
We're still gonna be able to like see what the startup would be like, even if the system's down there. It's not actually.
Yeah, you'll be able to go through and do all the checks. You just can't actually start the reactors. Pre-startup checklist you can go through. Yeah. Okay. Awesome, guys. See you next week.